Welcome. This is the first problem in our practice set for lecture 5-6, where we were actually covering Kepler's law. This problem says that Neptune is an average distance of 4.5 times 10 to the 9 kilometers from the sun. Estimate the length of the Neptunian year using the fact that Earth is 1.5 times 10 to the power of 8 kilometers from the sun on average. All right, so we're comparing the period and average distance of two planets. That's going to be Kepler's third law. So first thing I'm going to do is I'm going to go ahead and write out Kepler's third law with subscripts that represent Earth and Neptune. So I'm going to go ahead and write it like this. I'm going to say that that the period of Neptune over the period of Earth, so the ratio between the period of Neptune and the period of Earth squared, should be equal to the ratio of the Earth's average distance from the sun, over Neptune's average distance from the sun. Actually, let's go ahead and make that Neptune over Earth, just to make sure that we have. So if I have Neptune here, I need Neptune to be here. The cube of that ratio. All right, so Newton's third law says that the square of the ratio between the periods is equal to the cube of the ratio between their average distances from the star. All right, that said, there are certain aspects of this that we can plug in and then go ahead and solve, but because I know that we're looking for Neptune's period, I'm going to go ahead and solve this equation for Neptune's period before I start plugging anything in. That said, I'm going to go ahead and take the square root of both sides. That's going to leave me with the period of Neptune over the period of Earth is equal to the average distance Neptune is from the sun over the average distance that Earth is from the sun to the power of 3 over 2. This is the result of me taking the square root of both sides. From there, I'm going to go ahead and multiply both sides by the period of Earth, which if we're taking this in terms of years, the period of Earth is just 1 year. So I'm going to have Tn is equal to 1 times, and I'm going to go ahead and plug in the average distance that Neptune is from the sun, 4.5 times 10 to the power of 9 over the average distance that Earth is from the sun, 1.50 times 10 to the power of 8. Units don't matter so much in this ratio because when you have ratios, the units cancel out. And this is to the power of 3 over 2. So we are going to need a little bit of a calculator help here. And when we plug in 4.5 times 10 to the power of 9 over 1.5 times 10 to the power of 8, and we raise it to the 3/2 power, then we should get that the period of Neptune is equal to about 164 Earth years. Now, the thing is that we only have two significant figures on our value for Neptune's average distance, so I'm going to go ahead and write this as 1.6 times 10 to the power of 2 years. We'd say that that is the length of a Neptunian year in terms of Earth years, about 1.6 times 10 to the power of 2. Good luck. I'll see you guys in the next one. This is problem 2 in our 5-6 practice set. It says the asteroid Icarus, though only a few hundred meters across, orbits the sun like the planets. Its period is 410 days. What is the mean distance from the sun? Okay, so about 100 years after Kepler, Newton used his law of universal gravitation and his second law of motion to kind of combine with Kepler's third law to derive this kind of alternate version of Kepler's law that utilizes the gravitational constant and the mass of the sun. That said, we have this form of Kepler's third law that is the period squared is equal to r cubed. Now, this r is specifically the mean distance, so sometimes you'll see it as s in some equations, but in this case, the capital R is our mean distance, just trying to get you used to different notations. If you multiply this then by 4 pi squared over big G times the mass of the sun, and so mass of the sun is usually shown by a circle with a dot in the center, then you can use this relationship to find the average distance that a planet or an asteroid might have in its orbit given its period. So we are given its period, but the problem with this equation is that we are actually using big G, and so big G requires us, if we want to just use the 6.67 times 10 to the negative 11 form of big G, then we need everything to be in SI. So the first thing I'm going to do is I'm going to go ahead and take my 410 days, and I'm going to convert that really quickly over to seconds. All right. So the way that I'm going to convert that to seconds is I'm going to multiply that by 24 hours per 1 day, and then multiply that by 60 minutes per hour, and then multiply that one more time by 60 seconds per minute. All right, and that should give me how many seconds are in this period. So I'm going to take that 410 in my calculator. I'm going to multiply it by 24, multiply it again by 60, and multiply it one more time by 60, and that should give me about, let's see, 3.5. Let's go to three significant figures. 3.54 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. Okay, times 10 to the power of 7. Awesome. So that's how many seconds we have in this asteroid's period. So that's going to be equal to t. All right. So now, given that, let me go ahead and solve for r over here before I start plugging in extra stuff or plugging in any values for pi or g or m or t or anything like that. I'm going to go ahead and then just multiply both sides by the reciprocal of this quantity so I can get r cubed isolated. So that's going to be t squared times big G times the mass of the sun over 4 pi squared. Now that should all be equal to r cubed. And then if I go ahead and take the cubed root of this whole thing, then what I can say is I can say that r is then equal to, and I'm going to say it's equal to the quantity t squared times G times the mass of the sun over 4 pi squared to the power of 1/3. And that's the same thing as to the cube root. All right, so now I actually do know the value of everything inside of this quantity here. So let me I make that clear. We have t is 3.54 times 10 to the power of 7 seconds. And then G, often given to you on formula sheets, is 6.67 times 10 to the negative 11 meters cubed per kilogram seconds squared. All right. Now, the mass of the sun, one that you might want to remember, the mass of the sun is going to generally be given as 2 times 10 to the power of 30 kilograms. And then one more thing, depending on whether or not what kind of calculator you're using, of course, we're going to try to use the closest value to the actual of pi as possible. So 3.14 might be fine. Since we're only going to take this to 3 significant figures, 3.14 should be more than good. So that's going to be equal to pi. But I'm going to do a lot of this work in my calculator. So I'm going to go ahead and take my value for t. I'm going to square it. And I'm going to multiply it by 6.67 times 10 to the negative 11. I'm going to take that value and I'm going to multiply it by 2 times 10 to the power of 30. Okay, from there, I'm going to go ahead and divide that by the quantity 4 times pi squared. All right. The value that I get there, I'm going to go ahead and take the cube root of. Okay, so I'm going to raise all of that to the power of 1/3. All right, that gives me, and to 3 significant figures, that gives me a average distance of 1.62 times 10 to the 11 meters. And since we made everything in SI, we know that that's going to be meters, and that's all that it's asking for here. Good luck. I'll see you guys in the next one. This is problem 3 in our 5-6 practice set. Planet A and Planet B are in circular orbits around a distant star. Planet A is 7 times farther from the star than Planet B is. What is the ratio of their speeds, VA over VB? All right, so we've done this a little bit before in this playlist where we're looking for tangential velocity of an orbiting body around a larger mass. And we do that by setting Newton's law of universal gravitation to centripetal force. And when we do that, we solve for v, the tangential velocity, then we get this equation that I'm about to write below. So v is equal to the square root of big G, that's the gravitational constant, times the mass of the object that we're orbiting around. So sometimes that's a star, For planets, it's usually a star. And then we're going to divide that by the distance or the average distance of the orbital radius. So in this case, it's going to be r sub whatever planet we're talking about. So for planet A, its tangential velocity, capital A, is going to be equal to the square root of big G times the mass of whatever star it's orbiting around over its average distance from that star. So this is going to be r sub A. Now this is going to be the same thing for V sub B, except instead we're going to use r sub B. So V sub B, or the tangential velocity of planet B, is going to be equal to the square root of capital G times m over r sub B. So the only thing that's different here is the actual mean distances. Now what's special about this problem is that it tells you that the mean distance for planet A is 7 times the mean distance for planet B. So I'm going to actually go ahead and show that now by getting rid of r sub A and just writing 7 r sub B. All right. So if I want to go ahead and take the ratio of V sub A over V sub B, then I can set this equal to the square root of capital G times m over 7 times r sub B all over the square root of capital G times big M over r sub B. And what I'm going to do in this ratio is I'm going to go ahead and cancel out everything that's the same on both the top and the bottom of this ratio. So that means I can cancel out big G and cancel out capital M on top and bottom. And then I can also cancel out r sub B because that's also the same on both top and bottom. And so then what I'm left over with is the square root of 1 over 7 over the square root of 1. All right. And this is going to be the same thing as the square root of 1 over the square root of 7, which is going to leave me with just 1 over root 7. And that's where I'd probably end this. This is going to be the ratio VA over VB. Good luck, guys, and I'll see you in the next one.